Okay, thank you, Dorte. And as I was telling Dorte, there won't be much universality in my talk, just an approach for dealing with three clusters of nuclei within an ab initio framework. So, well, I will start with the general introduction on the type of approach that we use to describe nuclei and their dynamic properties. Then I will move to the microscopic ThreeCluster problem, the general define what the microscopic ThreeCluster problem, what I mean by it. Then I will introduce a little bit more in detail the kind of approach that we use to describe a system of anucleons that is partitioned into a cluster of A-2 plus 2 single nucleons. And then I will show some applications to helium-6, and I will finish with some conclusions and an outlook. Okay, so this is a very general introductory slide. So our goal is, at the end of the day, to develop hopefully a fundamental theory for the description of dynamic processes between nuclei, because we would like to tackle important milestones, such as being able to describe accurately landmark reactions for astrophysics, such as those, for example, in the PP chain that lead to the production of the high-energy neutrinos from the boron beta decay, which can be observed on Earth and come from the after the production of boron in the beryllium-7p gamma reaction. Or even more boldly, one would like to predict reactions important for the creation of elements with the mass larger than 8, like carbon and oxygen in stellar nucleosynthesis. Then, of course, I work in a national laboratory, so we are interested in being able to describe reactions that are important for fusion energy generation, not only the famous DT fusion, but also other fusion processes, for example, the TT fusion, which has a 3-body breakup channel at the end, or, for example, the Bremsstrahlung process that is one of the branches of the DT fusion, and they all occur in a plasma during a fusion process. And then, of course, we also would like to describe exotic nuclei, which are these systems with unusual ratios of proton to neutron that live at the boundaries of our nuclear landscape, and they are now they will be the object of study of experiments such as the FRIB here in the US, in Michigan. But then, of course, ultimately the desire would be to help unveil the true nature of the nuclear force by doing ab initio calculations. So why do we need such a fundamental theory? Well, the thing is that fusion reactions are difficult and sometimes are impossible to measure at the low astrophysical energies of interest. And well, there are two main reasons for this. First of all, the fusion process operates mainly by tunneling through the Coulomb barrier, because the two nuclei are positively charged, which means that the rates drop almost exponentially while going towards the low energy region of interest, which means low rates and then, of course, difficulties in measuring these. And in fact, the cross-section, the interesting part of it is what we call the astrophysical factor, or the S factor. Once we factor out the exponential, which regards the tunneling through the Coulomb barrier. Another problem is that in a laboratory, the projectile and the target, they are not fully ionized, so they have electrons that are bound to it, and because of that, the Coulomb barrier that the two nuclei in effect observe when they are fusing together is lowered by the presence of these electron clouds, and this enhances the S factor at low energy, and so it masks the, let's say, bare nuclear cross-section or S factor we are interested in. And so this is another issue that for which we would like to have a fundamental theory. So, well, this is extremely general. So in a nutshell, what we want to do is to calculate the properties of a system of A nucleons in terms of A point-like fermions that interact through free space forces. Yes?
Turn you back to the previous slide and ask about the screening, electron screening.
Mm-hmm.
See, the energies which you show there for helium are relatively much larger than the binding energy of the electrons in helium. So I assume that when they fuse, the nuclei are very close to each other, so the electron screening won't be very important. The other thing which surprises me is that the bare S factor is smaller than the observed one. I assume the electron screening leads to lowering of the potential barrier.
And then it enhances the cross-section.
Should be enhanced.
Yeah, that's exactly the case.
Right.
In fact, the experimental S factor.
What happens at those images? Because the images are
Well, what happens is that the screening,
because
it happens.
10 kV or 20 kV energy, so it's much larger than the binding energy.
I mean, okay, this is sort of an atomic question that I haven't thought about myself that deeply. What I can say is that one can observe these. Is not so easy to observe it. It always happens at fairly low energies, and one can see it mostly in those systems for which one can go fairly low in energies, like the helium-3, helium-3.
But then it seems to me it's too high still to see electron screening at that energy. That's the reason which puzzles me.
You think
Because
it's still too high in energy?
The electron, it's about how much? 20-something electron volt.
I don't have now an answer for this. I would have to think about it. The thing is, experimentally, this is what one notices, and clearly there is an enhancement of the cross-section, which is which has to do. This is, by the way, an extrapolation from higher energy results done with the very approximate theory.
Okay.
So it's not a calculation that I made. This is what people usually quote as. Yes. So this is actually the danger of it, that basically we don't quite know what's going on here, and so it would be nice to be more predictive. Yeah, that's exactly the issue.
The real question, I mean, are you talking about two helium atoms coming
No.
together?
Yeah. Okay. So this is the problem. This is the problem. So what?
I mean, the screening we're talking about comes from a star or something like that, right? It's
Okay. We need to distinguish the two things. Of course, in stars there is also a screening, but it is plasma screening, and the electrons are in the continuum. I mean, it's all a. Okay, so here in a laboratory, what happens is that in practice one uses ionized atoms or molecules, and so this type of screening is different because some of the electrons are still bound. So. While the former is fairly well understood, the latter is not as much. And so this is actually one of those areas of intersection between nuclear and atomic physics, which is quite interesting.
Is it possible that S bar actually goes up and there's better agreement than, because it's just extrapolated?
Well, actually, so I will not show for this reaction, which I haven't tackled myself yet, but another one, which is the D-helium-3 fusion, also shows electron screening, and there we find that actually the S factor does go.
Okay.
Well, okay, I don't remember exactly the scale, but it doesn't rise like that. Okay, yes, so as I was saying. Of course, it is true that protons and neutrons are not elementary particles, obviously, but at the energy scales we are interested in for nuclear physics, they do represent the relevant degrees of freedom for our problem. On the other hand, the interaction among them that emerges from QCD, not unlike, let's say, van der Waals forces emerge from electrodynamics, and well, ideally we would like to to use interactions that are guided by quantum chromodynamics and using the techniques that were proposed initially by Weinbergs by deriving them from the, starting from the chiral Lagrangian. Well, nuclear forces, so in nuclear physics we have a sizable component of the nuclear force, which we cannot neglect. And this is one of the characteristics. And the other characteristics is that they are, they have a very hard core at short ranges, which makes calculations difficult. The other thing is that we want to describe the system, we want to describe all possible excitations of all nucleons in the system, so all their configurations, and this is an example of how the size of the problem can grow computationally when you are increasing the size of the model space that you're using, and this is the dimension of the problem. So you can see that for nuclei like carbon-12, the problem can easily reach the billion for the dimension. So the fact that we are dealing with the hardcore Hamiltonian is an issue, because we cannot work in you know, enormous model spaces because of the dimensions, and so we would like to keep them as small as we can. That is why we often use unitary transformation of the Merrill Hamiltonian in order to soften it. And recently, well, one of the approaches that is, let's say, going on these days is the similarity renormalization group, which basically allows to decouple high and low momentum components of the nuclear interaction, and therefore being able to reach convergence of the calculation within the model spaces that we can achieve computationally. Okay, so how do we actually tackle the whole problem? Well, we start with an approach to describe the static property of like nuclei for first principles, and in particular with the ab initio-Courant model approach, and this is basically if you want a configuration interaction approach in the harmonic oscillator basis. And we work in the harmonic oscillator basis because it allows us to deal with to be able to describe the translational invariance of the system. That's the utility of it. And in our approach, we include all possible excitations of all nucleons up to a certain maximum for the total excitation of the system. So that's how we expand our model space. And the poster child of this approach is, for example, the energy spectrum of the nuclear states for the boron 10 nucleus, which is nucleus with 5 protons and 5 neutrons. And here, here there are 3 sets of spectra. There is the experimental spectrum in the middle. Then there is, on the right-hand side, the spectrum obtained only with the nuclear-nuclear interaction, and on the left, the spectrum including also the trinucleon force. And the thing that I would like you to notice is that the correct ordering of the first 2 bound states of boron 8 is recovered only once the trinucleon force is included. Basically, with the nuclear-nuclear force alone, we find a 1+ ground state for the system rather than the observed 3+. So this approach, yes?
I simply don't remember this particular project many years ago. I'm wondering, was the induced trinuclear forces included in the calculation?
Yeah,
this question.
Mm-hmm.
Yes.
Yes.
So they were. Second question: was the error in the binding energy?
Yeah, I don't. So this is there aren't the name of the authors here, but I was not one of the authors. I don't recall. We can discuss it later. Yeah, it's probably okay, but certainly not as much as you know. The fact that the 2 levels are inverted, that could be distinguished by from the numerical error. So,
what I remember, the error in the binding energy is of the order of several MeVs, and there the energy differences are much smaller.
Okay, we can check, but I believe that they could distinguish between the 2. Yes. Yes.
Quick question, maybe a dumb question. So a priori, is there a reason that if we to say that if we didn't include the 3 nucleon interaction, that the 1+ state, we should expect that to be the lightest? I mean, why would the 3 nucleon really lead to such a shift between the spin 1 and the spin 3 state?
Oh, well, my likely explanation is that the spin orbit force has an important role on this state, and basically by including the 3 nucleon force, you increase the strength of it, and that's why, yeah, that's what I think is going on. Then I don't see an a priori reason. Oh, yeah, so
States that when you include the 3 body.
Well, it is not something that happens all the time, but this is something that was observed also with the Green's function Monte Carlo, for example, using the AV18 and Illinois 2. So these are situations. I mean, overall, the 3 nucleon force does improve the agreement of the spectrum, at least for the low-lying states in general, because, I mean, having the right spin orbit force, or closer to reality spin orbit force, does help in yeah, okay.
Sophia, as you know well, I mean, the 3-body force doesn't make any sense without specifying which NN force you are.
No, this is okay. I agree with you. Yeah, sure. Specify what this was.
This transparency is nice for propaganda purposes, but could you be a bit more specific and
sure.
Which NN force?
Yeah. So this was this was the chiral N3 law of anti-Mach-Light, and this was the N2 law in the local form that
so
they are not consistent. They are not consistent. And what else? This was done with the Lee Suzuki effective interaction. So the 3 nucleon force were induced were included, and yeah, and the 3 nucleon force was actually fit to Inium-4 and some other properties of fission nuclei. Okay. So, in order to describe dynamic properties between nuclei, then we use the resonating group method approach. So what we do is that we use basis states that are basically 2 nuclei in relative motion with respect to each other, and in which we describe the 2 nuclei with the approach above, and then we solve for the relative motion. And so this approach has been successful already in describing reaction of various kinds, starting from nucleon-nucleus scattering to more complex reaction like transverse reaction, like the D-Inium-3 or the DT fusion reactions. And as you can see, so here I'm showing the S factors for these 2 systems. Here again is the electron screening that can be observed. I was mentioning it earlier, and here this time is our calculation, and our calculation is directly for the bare S factor, and we do not see this rise of the S factor. It keeps going down. So we were fairly successful in describing light nuclear fusion reactions, but these are not yet truly fundamental calculations. Well, for starters, these were calculations done only with the nuclear-nuclear interactions, so there were no induced 3 nucleon forces and no real 3 nucleon forces. And second, in order to describe the deformation of the deuteron and its, let's say, virtual breakup at higher energy, we basically discretized the continuum using several pseudo-excited states of the deuterium in our basis. So that's also not ideal.
What are the different curves in the lower plot?
This is exactly the convergence, let's say, of the calculation with respect to the number and the type of pseudo-excited state of the deuteriums. So in this case, there were 2 channels that are included in the calculation. So.
Do you understand why you're too high in the resonance peak?
Oh, well, it's, as I said, this is just an interaction. There is no used force. I mean, there are a lot of issues still. So
there is no physics like that's going on there.
I wouldn't, at this point, I wouldn't make huge claims about the physics. Okay, so I think it's too early for that, but okay.
Since you use harmonic oscillator wave functions in the shell model calculation, how were you able to fit in the deuteron?
Yeah, this is not.
Into the harmonic oscillator basis.
I mean, the deuteron is not. Is not a huge deal. You can use a very large number of harmonic oscillator basis states because just a two-body system, and then you can describe the wave function to a fairly decent distance.
So you
but
do the shell model for each partner, and then
yes,
the
that's exactly.
interaction between partners you do.
That's correct.
separate.
That's correct. But
You still need the wave function of the deuteron to be represented.
yeah, no, but okay. As I said, for the deuterium, the wave functions are fairly well represented, being just a two-body problem. But as I said, ideally, one would really like to have two, a neutron and a proton. Ideally, one would like to solve a problem which we has, for example, helium-3, a neutron and a proton, a three-body kind of system, and then let the deuterium, let's say, the bound states and the continuum of it appear on its own from that. Ideally, that's... okay, so, well, we are there. We are doing good progress, but we are not quite there. We need to extend this approach to include all the three nucleon forces that we need to include. And another technical development that we are working on is to include states of the compound nucleus. So we are expanding the basis by including states of the compound nucleus because when the two nuclei are fusing together and are approaching each other, these kind of basis states are going to be more efficient in describing the system than cluster states. So it's going to help the convergence of our approach. And the next, we would like also to include the ThreeCluster states to be able to describe, for example, ThreeCluster states in the continuum, or to better describe the deuterium, as you mentioned before. So in this talk, I'm going to talk mostly about this development, the treatment of ThreeCluster states. But before starting with that, I would like just to give you a snapshot of the other 2 points that we are working on. For example, we have been working on including the trinucleon force in our calculation. So to be specific, once again, here is a not fully consistent calculation. And to my, let's say, not completely our fault, the N3 low trinucleon force is sort of kept as something precious that they will not release until they are done with it. So, so the calculation is not consistent because this is the N3 law interaction event and F Mach light.
Why don't you use N2 allow two-body force to be consistent?
Yeah, well, yeah, that could be done. That could be done, certainly, yeah. That's something that we should do. We haven't done it so far, but you have a good point there. And then the trinucleon force is again N2LO, and we do include, when I say nucleon here, I do mean results that include the induced three-body forces. Okay, so as an example here is an effect of the, let's say, initial three-body force of the Hamiltonian in the last scattering of neutron on helium-4, and there is on the left an angular differential cross-section as a function of the center of mass angle for a fairly low energy of the incident neutron, which is 1.8 MeV. And on the right instead there is the total cross-section, which is basically the integral given at each energy by the integral of the cross-section on the left. And as you can see, one can notice sizable effects of the trinucleon force, especially in the low energy region. The trinucleon force is really important to get the peak. But it can be also seen in the differential cross-section because it affects the angular distribution. If one, of course, is at low energies, then at higher energies, the differential cross-section does not show much of a difference
but
either.
If I look on the left, the red curve, it's basically below the blue curve. And the right plot is the opposite. Because I obtained the right one by integrating over the angles. So how do you explain that?
Well, this is a logarithmic scale,
Oh,
and
the
yeah,
random dominates the-
yeah, it's not a very good. Yeah, my postdoc has this weird way,
So
but
it's
anyway,
basically fourth
yeah,
scatter.
yeah. So it's this region here that is really dominating.
What do you need?
Here we are going up to J = 11 for the partial waves in the differential cross-section. Of course, for the differential cross-section, it converges decently rapidly. The problem are polarization observables. Then you have to go to higher partial waves, yeah, certainly they are more sensitive.
Myself, I'm surprised at this low energy the cross-section.
Okay, at this low energy, probably less, but at this low energy, yeah, sure. At this low energy, probably less, but you know, we just scanned the whole system.
For some reason?
I
Do
did.
you have absorption, optical potential?
No, we don't. This is just coming directly from the calculation.
Sophia?
Yes.
So did you look at phase shifts in this?
Oh yeah, I can.
Did you compare to the work that was
Sure.
done by Joe?
I can show them at the end, perhaps. I can show. Oh, compare directly.
Yeah.
With
Jerry and Joe and everything?
We haven't put them on the same graph yet, but yeah. With Jerry, sure. With the Hermetrics analysis, I can show you later. Okay, remind me, please. Then the other thing is the importance of states of the compound system. So my caption here is fairly vague. What these are angular differential cross-section for deuterium scattering on helium-4 at two different energies, one low and one higher. And the model space that we were using was deuterium, once again with the many pseudo-states in several channels, and then instead the helium-4 just in its ground state, okay? And now this is the dashed blue line. In the red line, we increased our model space by including also several excited states, eigenstates of the lithium-6 within the no-kosher model, okay? So this has the effect of basically mimicking the polarization of the system, and it helps convergence at low energy, where it helps when the two nuclei get close together and A-body correlations become more important. And as you can see, there is a very large effect when you are at fairly low energies. Then at higher energy, the effect decreases, but this is an important contribution to the model space. Anyway, going on. So we have been able to improve our description of binary system, but that's not all. We would like also to describe. Yes.
Sorry interrupting you, see, but I'm thinking about the previous.
Yeah, sure.
You see, lithium-6, it's a typical cluster,
Mm-hmm.
you see, which is alpha plus.
Yes.
And you said that you had to introduce extra states of lithium-6.
Mm-hmm.
Which are those? Because I think the first two states, you see, they're pretty well explained in the cluster model. Is that true or not?
Yeah. No. So that's.
So what extra states you have to?
Okay, that's the point. What we use is basically a cluster model, okay, in which we have a deuterium and an alpha particle. And we see that that works well, except that because we are not including excited states, let's say, of the helium-4, because we do not.
Helium-4, you said?
I know it's very bound, but at the same time, in the cluster models, in order to mimic the A-body correlation, short-range correlation, what happens is that one has to include several excited states of the clusters, okay? Because cluster model will describe well cluster correlations, and which happen at medium to long range. But when it comes to very short ranges where full A-body correlations are important, then in order to mimic those, in cluster model one has to put a lot of states of the two clusters that are involved.
You mentioned lithium-6 also.
Yes. So exactly. So in order to, instead of doing that, which is computationally not very clever, we couple, we use the cluster model, and then we couple to it eigenstates of the A-body system, which are calculated within the kosher model, and so they are lithium-6 states. So we increase the basis.
But do you include the ground state? And
Yeah.
So you have a non-orthogonal basis?
Yes, and we orthogonalize it, and we do all it needs to be done to yes. Okay. Yes, one point that I forgot to mention is that the six-body correlations are important not only for cross-section observables, but also for the binding energy of lithium-6. Basically, with respect to the cluster model, one gains one extra MeV of binding once putting the six-body correlations. Yes, okay, so the next goal. we would like to describe also three-body breakup reactions and systems that have a three-body decay channel, like famous Borromean New Clay, and probably everybody knows the story about the symbol of the Borromean family, which was three rings connected together. And if you break one, the whole system falls apart, which is exactly the case with the Borromean New Clay. When you take one of the clusters apart, the whole system falls apart. There are various of these nuclei. Helium-6 is the lightest, and then there are helium-11 and so the lithium-11 and so forth, and so forth. And the lithium-11 is perhaps the most famous because what happens is in this nuclei is that the two neutrons orbit at a distance with respect to the core, forming something of a halo. And in lithium-11, the extent of this halo is such that the radius of it is comparable with lead. Okay, so now to tackle this kind of problem, we have to solve the microscopic three-cluster problem. Okay, and here to describe the intrinsic motion of three nuclear fragments in relative motion with respect to each other, we use so a system of anucleon. We use an ansatz of this type, in which these are unknown amplitudes that have to be determined and that represent the motion in the relative Jacobi coordinates of the system. And then we adopt a three-body channel basis, which is described here and is given basically by the product of the three intrinsic wave functions of the three clusters, multiplied by delta functions in the relative motion. Okay, so this is just a trick which comes from the fact that while these are microscopic, you have to think of it as microscopic antisymmetric wave functions of the systems. So while these are antisymmetric, the overall three-body channel is not, because we are still missing the exchanging between clusters. So we have to antisymmetrize it explicitly, and so of course in order to factor out the wave function we are interested in, then we just introduce these deltas. Yes?
Now, in the previous cluster, you made the case that you have to introduce lithium-6 internal states.
Here
are you going to introduce that in this one also?
That's exactly the same thing.
Because you need the coordinates x and y, so how are you going to extract them from lithium-6?
No, that's not that's not a problem actually. That's not a problem.
Well, you
because
have to separate lithium-6 in 2 or 3
No,
parts.
that's
whatever nucleus you are looking at, and then it's kind of arbitrary doing that, isn't it?
I'm not following the.
I think you see here when you construct the basis, it's pretty clear. You see, you take products of 3
Yes.
ground state wave functions,
Yes.
antisymmetrize, and then you put the amplitudes and find the
Yes.
equations.
Yeah, what I do is not, I do not separate the the helium-6 in this case. What I would do is take, calculate the couplings between the Hamiltonian couplings, for example, between the helium-6 eigenstate and this basis, and including in the model space.
Some non-diagonal type terms here.
Certainly, certainly.
Are you going to show how you do this?
Well, I have not, so this is not the real topic of the talk. This is something that we have done for the alpha.
No, but you said that that's important.
No, sure, and it will be done also here. That's the ultimate goal. It has not been done yet. So right now we are working on just the three-cluster basis. Okay. I completely agree with you. No, but it is not going to be very difficult. Maybe in the rest of the talk.
Well, I'm wondering how you do it.
Yeah, I will. Sure. Okay, so this is the basis, and now once one projects this, the Schrödinger equation onto the channel basis, so yes, on this channel basis, one obtains an integral differential equation for the amplitude that we are trying to find, and in which basically, one observes the Hamiltonian, what we call the Hamiltonian kernel, and then there is an overlap or norm kernel, which are nothing else than the matrix elements of our a-body Hamiltonian and the overlap on the channel basis. Okay, so these contain all the structure information and the anti-symmetrization properties of the system. Okay, and then we have no, it's just, of course, just one.
You can remove one.
Of course, just one. Yeah. Okay, so now a convenient basis, of course, to expand the channel basis I presented before are the hyperspheric harmonics functions, which are basically, everybody knows, I'm sure here, the many-body generalization of spherical harmonics. So what we do is, of course, a change of coordinates from the Jacobi coordinate I showed before to hyperradius and hyperangle. And now, once we do this change of basis and we orthogonalize the equations I showed before by multiplying on the left and on the right by the inverse square root of the norm, and then project on the complete basis formed by the eigenstates for the hyperangle, then we end up with an hyperradial equation, a non-local hyperradial equation for these hyperradial amplitudes, which basically you can see here they appear in the hyperspherical expansion of the relative motion. Okay, so I make the ansatz of using hyperspheric harmonics, and then rather than looking for the G that I showed before, I really look for these hyperradial amplitudes, and then I assume that okay, this is the basis on which I expand. And then these equations can be solved using the microscopic arithmetic theory. So basically, what one does is to divide the region into an internal region or interaction region, and then into an external region in which, if the Coulomb is present, then it's the only interaction present in the external region. And then in the internal region, well, in the external region, the solutions of the Schrödinger equations are known, and if we are considering a bound state, then we know that asymptotically for a neutral system, for example, asymptotically the bound states will look like this, where this is a modified Bessel function in the upper radius. Instead, if we are considering scattering states, then the hyperradial amplitude will be proportional to the incoming wave, and then of course there will be the proportional through the scattering matrix to the outgoing wave. Excuse me?
You mentioned Coulomb interaction.
Yes, I said if Coulomb.
You shouldn't have the right Bessel function, you should have Coulomb wave function.
I said for a neutral system, it would be the Bessel. I said if Coulomb is present, but I am looking into helium 6, so Coulomb will not be present. In this case, it's a modified Bessel and hang.
Hyperspherical representation, the Coulomb function will be funny, right? Because it depends on how you separate the charges. And
yeah, certainly. They
they'll depend on the partial wave and so on.
Mm-hmm. Yes, they would have to be Whittaker functions in complex energy. Yes, they will be more complicated, certainly. Okay, and yeah, so in the internal region instead, one can use an expansion on a square integrable basis, and a convenient one are Lagrange meshes, Gauss quadratures, because as I showed before, our interactions, our Hamiltonian is non-local, so it's convenient to use these quadratures. Anyway, okay, the solution then is found by solving the previous equation in the internal region and imposing the continuity of the external and the internal solutions at the boundary. Okay, and the solution has to be independent of the matching radius, of course. Okay, so now more to the application. So we want to implement this microscopic ThreeCluster model when we describe the helium 4 within our ab initio approach. And here is, let's say, the disclaimer. So we haven't developed the whole full theory right now, so we don't have 3 nucleon forces in this case. We have only a nuclear-nuclear interaction, so that's not, of course, the desired thing. We are using SRG evolved current real potential to a fairly low momentum because that makes it soft. This fits the nucleon data accurately, but of course misses both current initial and SRG-induced trinucleon forces. Fortuitously, this is just fortuitous, the two effects mostly seems to compensate each other for very light nuclei. So, but that's not, you know, to be expected or anything. It's just a matter of luck. So the ab initio wave function is of the helium-4 is obtained with the no-core shell model, and as I said, expansion harmonic oscillator. The Pauli principle is preserved, translational invariance is preserved. We will be able to include trinucleon forces, as I showed earlier for the binary cluster. We can do it also here. And with this interaction, the binding energy of helium-4 comes out close to experiment. So it can give a good qualitative description of the system. And now the channels are antisymmetrized in full, and there are, you know, a bunch of permutation operators that one has to calculate in order to do the full antisymmetrization.
How come the binding energy is so close?
Because of these, that basically just fortuitously, the induced and the initial trinucleon forces, basically their effect kind of cancels out.
Fortuitously, you mean for this particular
lambda.
1.5?
Yeah, in the, you know, yes, around lambda 1.5 and 2 that happens. Yeah. It means nothing. I mean, I put it in bold. This is just by luck. I'm not claiming anything here. I'm just saying that, okay.
So by including
It's the first time they've
by including two digits after decimal point in this 28.22,
Yeah.
saying that the effect uncertainty is at that level, or?
Yeah, but okay, yes.
Oh, it's very worrisome, right? Because,
What is worrisome?
that you get so close.
I mean, why it's worrisome? It happens. It's not.
He worries a lot.
I worry a lot, yeah.
I mean,
there's a lot that you haven't included. And
No, Bira, you can take any other, you know, effective interaction. It can give you the binding energy of helium-4. That doesn't mean that it is the right interaction.
I don't care about every other interaction because in an effect field theory you are throwing away a bunch of stuff.
No, but okay, this is not effective. It's not the fault of the current real law. It's the fault that we are using the SRG.
I don't know whose fault it is.
But anyway.
I mean, that's my point. I mean,
No, but you must remember the plot. I mean, I think I have it at the bottom of the presentation, but I don't want to go all the way there. But if you look at the binding energy, I believe with respect to lambda, and here is the experiment. I think it goes, well, I am going by memory. It goes by this more or less when you do the n and only. And this is the region of lambda, I don't know, like between 1.5 and 2.2, I don't remember. There is a region in which that happens, but it's just fortuitous, and okay. Doesn't mean anything, except that when you are looking at the threshold of the reaction, you know, it will be more sensible. So since I'm just doing this calculation for the first time, I'm using an interaction that at least gives me the right binding energy of helium-4. That's all. Okay? There is nothing more.
But is that the spirit of this SRG? I thought
No.
was more to
No. The spirit of the SRG is that you have to put all the induced forces. And that's something that we're going to do. We are not there yet for the ThreeCluster model.
So you chose this region purely for convenience?
Yes, right now, yes. And I showed the 2 slides before in which I showed that we put all the induced and real forces. That's what we want to do.
And in that case, what do you do with
ultimately.
lambda? What do you do with lambda in that case when you actually do include all the induced?
It should not be lambda dependent. Of course, for the helium-4, I believe the plot in the case would be something like, I don't know, something like this, in which you get a mild dependence at the very bottom, in which in which induced 4 body forces start to play a role when you go very low in lambda. But other than that, you recover the unitarity of the transformation. Okay. So going ahead, how we do this? Well, so the formalism is general for any target plus 2 neutrons. But okay, so starting from the norm kernel, which is the easiest of the two, all we have to do is to calculate the matrix element of the antisymmetrization operator squared, which is just one antisymmetrization operator in our basis, okay? And then, of course, there are elements of this antisymmetrization operator which are just an identity, and then there will be, which give this obvious part in which you have a delta in the relative motion of the system. And then there will be many body corrections that come from the matrix elements of the permutation operators. And so here I have just these sketches for simplicity. There is let's say the alpha particle, and then there are the two neutrons. I use different colors because these two systems of nucleons have not been antisymmetrized yet. Okay, and then there will be the direct term, and then there will be a term so in which we will have the exchange of one nucleon from the antisymmetrized two nucleons to the alpha particle, but then there will be also corrections. This will not be fully antisymmetric unless we include also exchanges of two nucleons at a time, okay? And so here, this term corresponds to this expression, and as you can see here, I have replaced these delta functions with the expansions in harmonic oscillator radial wave functions for both the x and y Jacobi coordinates. And this is fine at this level because the matrix element of the permutation operator are localized. They are short range, so these expansions converge when you increase the model space. Same thing here. Now, how do we calculate these matrix elements? Well, we calculate them. One can prove that they are proportional to for example, in this case, the one body density calculated on the target wave function, and in this case, the two body density calculated on the target wave function. And this can be calculated fairly easily in a shell model code. Okay. Now, how do these things look like? So the interesting part is to look at the exchange part of the norm kernel, which let's say gives information about the Pauli principle. And of course, in a system largely like helium 4, for example, which is largely an S-wave nucleus, excuse me, the largest component of the exchange kernel is in the partial wave in which these two systems are in S-wave of relative motion, because of course one has to cancel the h bar omega 0 component that would violate the Pauli principle. But then, so here this exchange kernel you can see is a surface in 3 dimensions. That's what we obtain. And here it looks like it's symmetric with respect to the coordinates x and y, but in general it is not. For example, for the partial wave in which the two nucleons are in p wave, of course, then one has again for the y coordinate, one again sees the effect of the Pauli principle, but in x the norm kernels is drawn to 0. Okay, so here is, for example, a partial wave in which the system is in total angular momentum of the two coordinates is L equal to 2, and one would think naively that here the Pauli principle is not important, but we still see negative contribution of the norm kernel. So I guess the messaging is one cannot neglect the Pauli principle, which is fairly obvious, but okay, that's what it is. Anyway, okay, so then for the Hamiltonian kernel, the story is pretty much the same. The part that is the most interesting is the one of the interaction. One has to antisymmetrize that, and once again one will obtain several terms in which there are interactions and exchanges, and again these are calculated using densities. In this case we will need also 3 body densities of the target. There is an extra term here that I have not described with diagrams, which comes from the interaction between the two neutrons when this direct part, so when, excuse me, acting on the norm kernel. So yes, basically just this component. And here, that part is special, let's say, because the direct part of it, when we don't have exchanges between within the alpha, looks like that, and in that case this term is proportional, so it's localized only in the x-coordinate, but it is not localized for the y-coordinate. In this case it's just a delta function. Okay, so here our typical approximation of using expansions in the harmonic oscillator is not the most appropriate. But so that's what we still do to regularize this delta function. But in this case, we use the model space that we use to expand this function is much, much larger than the typical model space for the rest of the system. Okay, so some results. As a warm-up exercise, we have calculated the bound states of the alpha plus 2 neutrons, and of course we found only one bound state. The bound state of helium-6 in the 0 plus channel. And what I'm showing here is a comparison between what we obtain from a 6-body diagonalization of the full Hamiltonian and no-Coshomonium space versus what we obtain using the cluster model, the 3-cluster model, in which we have the alpha particle just in its ground state. Okay, and this is a plot of how the ground state energy of helium-6 converges with respect to increasing the model space that we are using, and as a function of the frequency of the harmonic oscillator well that we use to describe. And as you can see, when one increases the model space, there is less and less dependence on the frequency, and one obtains a fairly stable result. And anyway, the final result is this one, minus 29.6 odd mega electron volt. Now, when we do the same calculation using the no-kosher model RGM, then we obtain this result, which is about 1 MeV short with respect to the no-kosher model, which is actually the same 1 MeV missing binding that I kind of mentioned before for the lithium-6. It is because we don't have this eigenstate of the helium-6 coupled into our basis yet. So this basically, what happens is that the differences between this six-body diagonalization and the cluster calculation are due to corporalization effects, basically. The fact that in a cluster model, to describe the body correlation, one would need to put excited states of the alpha particle, and we are not putting them in it. Instead, in the no-kosher model, they are already there. On the other hand, as Aurel pointed out, in an harmonic oscillator basis, it's not easy to describe the tail of a wave function that has a very extended sites like the one of helium-6, which is a halo nucleus. So in this case, the wave function of helium-6, they are truncated, they have the wrong asymptotic behavior. So this is not the case for the cluster model, in which, of course, we obtain by design the right asymptotic behavior for the wave function. What I'm showing here are these 3 of these hyperradial amplitudes that appear in the relative motion wave function of the helium-6. And actually, the convergence of them with respect to the size of the harmonic oscillator space that is used.
Do you have numbers for the helium-6 binding energy without your antisymmetrization?
No, actually, that's probably going to be horrible, because
that's the question how bad that is.
Well, it's going to be deeply bound. I mean, because you are violating the Pauli principle, it's going to be deeply bound, I assume. And because you see, well, I am going to show you again this picture. Look at the sides of these exchange. So what they're saying.
Eigenvalues of the norm operator.
Not on my computer, but certainly these are basically close to 1. When you take the eigenvalue of the norm, or close to 0 when you take the eigenvalues of the exchange part of the norm, they're close to 1, meaning that. How
many of them are close to 1?
If a large number, it's
10, it's 100, it's 1,000.
On the order of, depending on the model space, 50, I don't know.
Yeah, so that
it's huge.
How important
yes.
Is it's very important.
I just would like to see the effect in observable. That's all.
Okay. So that's a good point. We can do. Actually, to be honest, no, that's not actually. It's not that easy in the sense that when you violate the Pauli principle so violently, then when you do the Hermetrics theory, it's going to just give you crazy nuts results. Yes, it just gives you spurious states. The norm becomes negative. What's the word? You know, you get the negative eigenvalues of the norm. It's a disaster. So it's not that easy actually. But okay. So where were we? Okay, yeah. So now I showed you the let's say the final result that we obtained for the largest model space. Here I wanted to show.
Can I ask you, see, concerning this one MeV
yes.
between the two? You see, so one way is to include these states, you see, the helium-6 in this particular case will be, and that will help you. But you might try to introduce the excited states of the alpha in this case, and by using perturbation theory. The question is, you see, how much you need. I would expect that probably the first 0+ will do.
Well, I
because
can.
The rest of them are either
I can show.
and so on.
I have actually a picture for the N-alpha system, in which I can address that, in which we have done that, put the excited state of the alpha particle, and it's a slow convergence.
So you mean if you do second order perturbation theory, that's not enough?
I'm afraid, yeah, you need many excited states, unfortunately, not just
so
the first 0+.
Not
only the 0+. Basically, if you go through the spectrum of the helium-4 up to fairly high energies, on the order of 25 MeV, they show in there.
The core is strongly
yes,
polarized.
yes. So, okay, now these are just a couple of slides to show the kind of oh my God, I'm late. Convergence behavior of the system. Anyway, it all works well. Expansions in the hyperspheric harmonic, and also this extended size expansion. It's fine. This is just the probability density of the helium-6 ground state. Of course, largest component is in the S shell. Then there is a much like 1 order of magnitude smaller when the two Jacobi coordinates are in P wave. And then, of course, this is the typical, two-lobed probability densities for the helium-6, in which one has the separation between the neutrons and the separations from the alpha particle, and one can recognize, let's say, the cigar and the dineutron configuration of helium-6, obviously.
The contour plot is the same thing as the 3D plot on the left?
Yeah, it's just, yes, surface plot.
The probability of one, the short range configuration of the two neutrons and the extended one is basically the same.
Yeah, and this for this potential. And again, this is,
Not only this potential, I mean, what do you think the effect of changing this lambda of SRG is on these things?
Oh, it would be probably horrible. I mean, yeah.
Horrible meaning what?
Well, first of all, it's going to be, anyway, it will change the picture, certainly. It will change the picture. I mean, it's not going to be invariant with respect to lambda. I can get all kind of results. I haven't done it yet, but yeah. Certainly.
What am I supposed to do?
No, right now I don't want to draw any special conclusion. It's not the end of the story. Here is just to say we have this approach. In a first instance, if you use an interaction that kind of reproduces the alpha particle, it gives you what you would expect, okay? Then we have to put the right interactions in it. This is about it.
I think it's an interesting question because this large, the configuration where you have two neutrons like this is basically a quote-unquote Cooper pair, which is natural to expect, or to have two neutrons very close to each other. Probably if you increase the couple, you see probably that will diminish in probability.
Yeah, actually I have
it will be something like lithium-11. You see, where lithium-11 has this big size not because the two neutrons are together, but because they're opposite to each other.
Okay. So no, in fact, I cannot draw a conclusion on which one of the two configurations is more important at this level. Yeah, of course. No, of course. And I have actually a figure with the different lambda for the scattering. Anyway, so we've also done scattering calculations for the system. Here are a summary of the low-lying scattering phase shifts that are attractive. I've just put the attractive ones here. And we find several resonances. The first one is sharp in the 2+, is the famous first excited state of helium-6. Then we find the second 2+ resonance as well, and then also 1+ resonance. These two.
Find this
So they are defined with respect to the hyperradial function.
Observable.
They are not, no. I mean, one would have to calculate
So
cross-section.
how do you relate this to observable?
Well, okay, in the usual way, with the cross-sections calculations.
See, I know how to do this for two-body scattering.
No, it's the same, it's analogous.
I've never seen a cross-section.
No, it's analogous. It's, since the epispheric harmonics are the many-body generated.
You can write the formula.
No, it's been done, it's been done.
How you define the cross-section experimentally? You see, this is the thing which I don't know. You see.
Experimentally,
Yes,
what they
because
do.
you have to have an observable, so I don't know how you define
They just
it.
measure the.
How? You have two beams of neutrons, you see, and how?
No. What they do usually is to smash helium-6 on a big lead target, or they use transverse reaction.
But that's completely different from what they're doing.
Anyway, okay. So anyway, there is also a 1+ resonance. They are close together because they have a similar structure with the two, with the two Jacobi coordinates in P wave. Then we have also two resonances, the 2- and 0- negative parity. For the 0+, we don't find, an honest-to-God resonance at low energies. There is this question about the soft dipole resonance. So we find this 1- that keeps rising it very slowly. It doesn't have the typical, monotonic sort of growth of a resonance. So it's kind of hard to tell what that really is. It's hard to call it a resonance like it is for the 2+1, but anyway. So comparing to experimental energy spectra by basically looking at when the second derivative of the phase shift it becomes 0, and calculating their width as shown here, we compare to experiment, and here this is a new measurement in which they have just observed.
I don't think you have the right to do that. That's a two-body formula, not a three-body scattering formula. You cannot use it.
Okay. Anyway, this is what is done here, but bearing on the fact that it's probably not the right thing to do, still we find that relatively speaking, the two spectra are in good agreement also for what concerns their width. Okay, and again, convergences. This is a convergence in NMAX for several phase shifts. And here I have a result that was obtained for lambda 1.8 Fermi to the -1. And you can see that the results are different, but it's not changing the vision dramatically. It's not like a resonance disappears and another one appears where we weren't expecting. It gives more or less the same, qualitative behavior, but different, of course.
I think you didn't understand the point of my question. I mean, you are doing a unit. You claim you are doing a unit vector transformation.
No, right now I'm not claiming it.
No, that the SRG you use.
No. In this calculation is not unitary at all. I don't have induced forces yet.
Right, but eventually you are going
Yes.
to do it. And
Then you have the right to call.
but then you are going to preserve only observables. So my question
Of
is
course.
related to the fact whether those distributions that you showed before are observable. The question
okay.
here is related
Yeah.
to Aura's question. I don't know what the space shifts mean. Are they observable or not? I mean, so.
Okay. No, I agree. So one shouldn't. This is a mathematical thing mostly, and that's what it is. Anyway, it converges decently in the hyperspherical expansion. And regarding this potential here, while for the bound state we don't find any significant effect of this truncation that we do for the delta function, for scattering it can be observed when the two neutrons are in 1s0 partial wave, and the interaction between them is strong, obviously, and that happens for the 0+, and it happens basically at very low energies, and for example here, but it doesn't affect the qualitative behavior of the phase shifts. It's just, and okay, and then, well, fortunately conclusions because I'm late. Anyway, yes. The goal is to go beyond what I've just shown here, obviously,
How
okay, this is not very interesting.
do you know it's efficient?
Well, we have shown that it is.
Teasing you.
It is efficient for binary. So there were some questions. Oh, I apologize about this. So there were some questions that people had about the phase shifts.
Yeah, just this N alpha.
And let me see if I have them here. So here is actually to answer Aurel's question. Here, this is the neutron medium 4 phase shifts with respect to how many excited state of the alpha particle we include in the calculation. And there are from the 0 plus up to the second, well, the 1 minus with t equal to 1. And this is the kind of convergence that one obtains. It's extremely slow. Now here instead is the calculation in which we put directly also the excited state of the inium 5 while keeping all these excited states of the alpha particle to check, that they do not matter anymore. And as you can see, everything collapses. And this is the kind of agreement or disagreement, depending of how you look at it, with the Armetrix phase shift. Okay. This is with trinucleon forces, everything. And then there was another question, I don't remember. And about the lambda independence, perhaps. This is not going to satisfy Bira completely, but okay, it's a starting. Here is the again the N alpha phase shifts for 2 lambda values. They are unfortunately quite close, 2.8 and 2.0 and 1.88. But okay, here is then an only calculation. You see just a small difference. And then when you put the induced, it decreases. Okay, one could expect that. And then when you include the initial trinucleon force, there is a tiny bit more of a difference again. But the truth of it is that, changing lambda means also dealing with the harder interactions. So in principle, one should be careful about the model space one is using. Make sure that everything is really convergent.
In this last column, you also have the effective trinuclear interaction generated by the full,
everything is in it. Everything is in it except for body-induced or higher-order induced forces.
And so how do you know those are small?
For small systems like lithium-6, they have been found to be decently small for this type of lambdas. I don't have a proof here, okay?
Okay, and the other thing is, so you do this SRG evolution for the potential, but it's a unitary transformation.
Oh, for the operator, yeah, we do that too.
What about other operators?
There it is. I knew all these questions would come. No, I am saying, I hope I have a plot. There they are.
Okay,
So now, if you want to, you should do the.
Other operators, okay.
You should do it for all the other operators, and we have been doing this for the square root mean square radius and the total dipole strength. For now on the helium 4, and you can see here results done with the Baire operator. So there are 2 types of lines. The dashed is with the induced, so wave function obtained with the trinuclear induced, and the red is with the full trinuclear force. And then the symbols, they tell you which operator we used. So Baire operator, 2-body evolved operator, and 3-body evolved operator. And you can see that this is again a dependence lambda, and then here is the observable.
Is this a proton radius? Is this a
point
radius?
proton radius, yes.
And so here the value for the triton is something more like 1.6, no?
This is not.
Are you comparing to experiment?
I'm not comparing to experiment. I'm just looking at the unitarity of the transformation. For the triton is exact. It's just completely flat, whatever lambda you use. Okay. For the inu 4, excuse me.
So why is it wrong?
What do you mean why it's wrong?
Well,
I mean,
so the experimental value is something
because
like
this whatever. I think it's not.
maybe it's not the proton.
No, this is the root mean square radius. Excuse me, for the matter radius for the triton. For the inium 4, it doesn't matter because excuse me, matter radius. Apologize. Anyway, here you see that it curves up a tiny bit when you go to lower. But it's an effect that it is really small. It's 0.0 something %.
Okay.
So with this, let's thank Sofia. I think we already had a lot of questions in between, so we're just going to cut out the question section now and thank Sofia again. And then we should have all the three-body phase shift questions in the afternoon.
I think there is an explicit, about this issue of antisymmetrization, there is an explicit calculation by Andreas Nogga and Kamada from 2000 something where they looked at this for some systems. So
there is no cross section.
Okay, we can give a look. I mean, I haven't. Honestly, as I was mentioning, when you remove the exchange part, then it becomes a deeply troubled system because it becomes hard to solve the problem. But I can look what they have done. Maybe
I mean, I thought you recorded.